Welcome back, everybody. This is our video solution to problem 4 from Quiz 4, Spring 2023 Math 302 at Cal State Fullerton. And we are still working with the Euclidean algorithm, although the problem doesn't tell you that, at least not immediately. So in the problem, we're given two positive integers, a and b. We're going to denote the greatest common divisor of a and b by g. And let's see, c will be some common divisor of a and b. So immediately we know that c is less than or equal to g because c is a common divisor and g is the greatest common divisor. But we don't want to prove that c is less than or equal to g. In fact, we want to prove c divides g. So this is a stronger statement. This actually came as a porism, right, in Euclid's proposition 7.2. And so we want to basically reproduce that proof here. So how's the proof going to work? Well, the way everything worked here is we're applying the Euclidean algorithm to a and b. So if we apply the algorithm, it's going to look something like, so we have a is going to equal some quotient, and let's maybe we'll call this the 0th quotient times b plus the 0th remainder. Okay, so over here we know 0 is less than or equal to r, 0 is less than b. And then we go to the next line and we say, okay, so b is going to equal some quotient times the 0th remainder plus a first remainder. And now here we know that r1 is less than r. And then we'll swap over again. r0 is going to be some second quotient times the first remainder plus the second remainder. And r2 is going to be less than, oh, it's supposed to be an r0 up here, less than r1. Okay, so here we are. What we're doing is we are applying the Euclidean algorithm to a and b. Okay, and I keep going. Okay, and what's going to happen is at some point I'm going to stop, right? And so maybe I'm going to stop on the nth remainder, which means this would have been the n minus first remainder times the nth quotient, and this would have equaled the, I guess, n minus second remainder. Okay, we don't know what n is exactly, but at some point, right, you're going to stop. All right, and we knew that if we went any further, this would finish. And okay, so if this is where not only do we know that Rn is going to be less than Rn minus 1, but here, right, we have 0 less than or equal to Rn less than Rn minus 1, but also Rn divides Rn minus 1. Of course, Rn could be 1, right? That's a possibility, but it would still divide. Okay, so what Euclid tells us is that when we get to the end, the Rn we get is the greatest common divisor. Okay, so this would imply, right, and this is proposition 7.2 in Euclid, that Rn is equal to G, right? Remember G, we defined up here, is the greatest common divisor of A and B. Okay, so this Rn is equal to G. Now, our goal is to prove that a common divisor C must divide G. Well, let's work our way through this then. If C divides A and it divides B, well, if it divides B, it also divides Q naught times B, and so it will divide A minus Q naught times B, which is equal to R naught. And so C will also divide R naught. So let's write that down over here. So C divides A, C divides B implies C divides Q naught times B, and the combination of these implies that C divides A minus Q naught times B, which is equal to R naught. Okay, now we go to the next line. We already know that C divides B. We have that here. We also know that C divides R naught. So we're going to get that C divides Q1 R naught. And now the combination of these two implies that C divides B minus Q1 times R naught, which is equal to R1. And I go to the next line. And I say, well, I know that C divides R0. We have that from up here. I know that C divides R1. So that means that C divides Q2R1. And so now if I put these two together, I know that C divides R0 minus Q2R1, which is equal to R2. So in each step, I'm able to get that the C is going to divide the remainder. And so continuing in this way, we conclude that C divides Rn, which is equal to G. And there we go. So this is how we are able to use the Euclidean algorithm, right? Which wasn't stated in the problem, right? We didn't mention the Euclidean algorithm here, but we're able to use it to show that every common divisor of a pair of positive integers divides the GCD. All right, everybody. We will see you next time.